Good morning. It is Tuesday, March 22nd, and I really am here at Osborne Park making a video for my students over spring break. So hopefully you guys will actually watch it since I took my time for spring break to come in here and make it for you in hopes that we can get as much material covered for the exam as possible. Today's chapter, and this is kind of unique, we're going back to chapter 12 with chemical kinetics. It is big idea number 4, and it's the only chapter in big idea number 4. So after a huge big idea number 6, where it was like 4 chapters worth of material, we got one chapter that we have to cover. And what we're going to study is chemical kinetics, which is the study of reaction rates. And so you'll notice I have a clock there. So we're going to be working with time in this unit. Make sure you grab your textbook because we will be working some problems out of the textbook. I did try and put them into the PowerPoint as well in case you happen to have left your textbook at home, which at school, which I can actually see there are several back there on the bookshelf. Okay, so let's get started. For reaction rate, we are looking in the change in a concentration of product or reactant over a specific period of time. The time unit we'll typically use is seconds in most of these problems. When we're talking about concentration, remember, look for brackets, just like we use the brackets in equilibrium. That's going to mean we're going to be using concentration in molarity. And when we're looking at rate, for those of you in calculus, this probably will look a little bit familiar to you. We're studying change, and in particular, we're studying the change in concentration over the change in time. So when we look down there at the equation, we have the concentration of A at time 2 minus the concentration of A at time 1 over that change in time. Now over here out to the side, you'll see I've put in some units for you. Unlike equilibrium, where we very rarely had a unit, we're going to have a lot of units in this chapter, and you're going to have to maybe do a little bit of unit analysis to keep them straight. The unit on top is molarity, so that's where we get the moles over the liters. And then also on the bottom, we're going to have our seconds. So there are a couple different ways you can write this unit. You can write it as moles over liter second, which we have here. You can write it as molarity over second. Or you can even write it as molarity times the inverse second. So just be aware there are a lot of different ways you can see the exact same unit written. Our changes in rate can be positive or negative, although we're never going to work in the negative. We're always going to work in the positive. And so a couple little things I wanted to show you. First example, we have a equilibrium up here because we have the arrow going both directions. It says over time, 0.0024 moles of phosphorus trihydride is consumed in a 2-liter container each second of the reaction. So now we actually, if you look at that information, we have what we need to get to molarity, and we actually have what we need to get to rate because we know every second this is what's being consumed. What we want to know is what are the rates of production of the P4 and the hydrogen in this experiment? So what we're going to need to look at is how is the rate of consumption of the reactant related to the rate of production of the products. So first, let's get a rate of disappearance for our pH3, for our phosphorus trihydride. So start off with rate of disappearance. And we said that rate of disappearance is going to be the change in concentration of our pH 3 over our change in time. Well, they gave us concentration information because we have moles of pH 3 and we know what volume it's going to be in. So 0.0024 moles, and I'm just going to go ahead and do my molarity problem right here. And we know the time frame that we're looking at. We're seeing how this is changing every single second. So every second, this is the rate at which it's changing. Well, if we want to turn that more simply into rate, we're going to take our 0.0024 and divided it by 2. And we get 0.0012 moles per liter second is consumed. Or is used, or the rate of disappearance. There are lots of different ways that you can refer to that. Well, what we're going to find is we can relate the rate of disappearance to the rate of production or the rate of appearance of our products by using our balanced equation. And if you go up there and look at our balanced equation, we see that for every 4 moles of our reactants that are consumed, we're going to make 1 mole of our P4, and we're going to make 6 moles of our hydrogen gas. And so using those coefficients, we can come up with the rates of production. So let's look at our rate of production for our 2 products. And first, we're going to look at the rate of production of our P4. And what we need to do is relate this to the consumption of our reactant. And we said that for every 1 P4 that we make, we need to consume 4 pH 3s. So we produce P4 at 1/4 the rate that we consume our pH 3. Now, where do we get that 1/4 from? We make 1 P4 for every 4 pH 3 that we consume. So we produce it at 1/4 the rate. Well, we know the rate of our pH 3. We'll divide that by 4. And the rate of production of our P4 is 0.0003 moles per liter second, which it should make sense where you make a whole lot less than we consume of the pH 3. Now, we wanted to do the same thing for our hydrogen. And our hydrogen, if you look at it, for every 4 pH 3 we use, we actually produce 6 hydrogens. So same thing, we have our hydrogen coming up with its rate of production. And this time, we make 6 hydrogens for every 4 pH 3 that we consume. So it's the rate of production of a hydrogen is going to be 6/4 our rate that we had for our pH 3. And we're just, once again, those 6/4, that just comes from looking at our balanced equation. Whoops, let me get my 6/4 in there. And that ends up with a rate of production of 0.0018 moles, whoops, not liters up there, moles per liter second. So once again, these fractions that we're using are coming from the balanced equation. In the first fraction here, 1 mole of P4 is produced for every 4 moles of pH3 that is consumed. And for the hydrogen, 6 moles of hydrogen are produced for every 4 moles of pH3 that are consumed. And since we know the rate of consumption of our pH3, that allows us to calculate our rate of production of our products. So just kind of like doing a little stoichiometry problem in a sense. We're using our mole ratios again. We already talked about we will always be using rate as a positive quantity. Our concentrations of reactants always decrease with time. So what we have to do is when we write our change in concentration over our change in time, we actually end up throwing in a negative sign into the equation so that we keep the rate positive. Because otherwise, when looking at reactants, our rate would always look negative because we're always decreasing that concentration. So we fix that mathematically by throwing in a negative sign into our equation. Um, what we'll be looking at, though, is typically instantaneous rate or initial rate, the value of the rate at a particular time. We don't dive too deeply into the reaction. We want to look at it at a very brief moment in time. When we were looking at how can we impact the rate of the chemical reactions, what are they affected by? They are affected by time, and they're also affected by stoichiometry of the reaction, which species is being studied. Going back to that first example that I did, everything had a different rate of either consumption or a rate of production, and that goes back to that stoichiometry where we use that balanced equation to see in what ratio were things produced and consumed. So using all of this, what we can do is we can start writing what are known as rate laws. And this is actually pretty easy stuff. So let's start with an introduction here. This is something we already know. Chemical reactions are reversible. Now, the star is up there because in previous years I would do this before equilibrium, and so we didn't quite know what reversible it means, but this year we got it. We know what reversible means. And we know that after a period of time, we get enough product made that we start going back and having the reverse reaction occur. Well, going back to equilibrium, what we know about it are when we reach equilibrium, the ideal, the two criteria that we have to meet is the rate of the forward reaction has to equal the rate of the reverse reaction. And we had used that word rate before, but we never really talked about it. Well, now we're going to really see what that rate means. And we also know that the concentrations have to be unchanging. Well, when we're talking about rate laws, we really don't want to get to the point where we're actually having the reverse reaction occurring, because that starts making things really messy. Because not only are our reactions being used, they're being decreasing, they also start increasing because the reverse reaction occurs. So what we focus on is we want to focus our study of rates right here. Right after the reactants are mixed. And a lot of times it's called the initial rate, because we don't want to get any products to build up, because we don't have to worry about now we're both increasing and decreasing the reactants at the same time. That's a huge mess. So we have a very specific point in time we want to look at, right when that reactants are mixed together. If we choose conditions where we can ignore that reverse reaction, then the reaction rate will depend only on the concentration of the reactants. Highlight this, underline this, set this on fire, tattoo it on the back of your hand, something, because we are only ever going to work with reactants when we are talking about rate loss. The AP exam, they're going to throw products in there on rate law questions, and you just cross them out completely. Products don't matter when we are talking about rate loss. We only talk about the reactants. So this is a very generic form of a rate law. Every rate law always starts rate equals, oh, there's K, times the concentration of the reactant raised to some order. And that's what this N means. It's an order, and we'll talk about that in a second. K, unlike our previous K in equilibrium where it didn't have any units, this K can have some really complex units on it. So we'll have to work through that a little bit. Notice we are only talking about the reactant, and we are going to completely ignore the products. And also be aware that this is the simplest rate law. We could have, another reactant over here, and it could be raised to another order. This could just keep going on and on in the problem. It doesn't have to be just one reactant. It could be multiple reactants. Let's put a couple things up here. K is the rate constant. It is determined experimentally. So once we determine our rate law, then we can go on to come up with what our rate constant will be. N, and it's also, you notice I put an M up here. It doesn't really matter what you use up there. Some people use X, Y, Z, M, N, O. It doesn't really matter. It is the order of the reactant. This also has to be determined experimentally as well. This can be an integer including 0, or a fraction. I will tell you 9 times out of 10, or even 9.9 times out of 10, your order that's going to be up there is going to be a 1 or it's going to be a 2. Occasionally a 0 is thrown in there, but first order or second order are the most common ones that we run across. Once again, we have to determine that experimentally, or they have to tell us what order is going to be used. And also, once again, this law only depends on the concentration of the reactants. Don't care about the products whatsoever. Couple key points in rate laws. Let me just go ahead and post all these up. Whoops, wasn't too many. Once again, can't stress this enough. Products do not appear because we set the conditions so that reverse reaction doesn't matter. We pick our point in time so we don't have to worry about them. N must be determined experimentally. K can be calculated once the form of the rate law has been determined by using the data from an experiment. And the whole point of rate laws is we want to get to the mechanism by which this reaction occurred. So far in our chemistry career, we kind of think we take two chemicals, toss them in a beaker, and we get a product. Well, there's a lot of little elementary steps that have to occur. There are different bonds that have to be broken, new bonds that have to be formed. There can be even steps that occur in between our initial step and our final step that we never even see and we don't ever write a chemical reaction for, but they're part of the mechanism by which this reaction can occur. And so that's why we study rate laws, so we can figure out what was the mechanism. How did A plus B become C? What happened in that beaker? Um, Couple of things that, when we're doing rate laws, okay, there's kind of an order by which everything has to be done. The first thing you always have to do is come up with the order of the reactants. That is always step number one. That's the first thing that has to happen. Now, once you have the order of all the reactants, then the rate law can be written. So order first, then you write your rate law, and once you have your rate law, then the next thing that is a must that you have to do is you have to calculate the rate constant. You have to come up with K. So every single problem we do, no matter what kind of method we're using, this is what has to happen. First, we got to get the order. Second, we got to write the rate law. Third, we got to calculate K. And fourth is whatever. There's lots of different problems you can do after you have those three things set up. Once you've got the order, the rate law, and the K, then basically you can do whatever you want with the problem. There's lots of different things we can calculate. So order, rate law, calculate K, and then whatever. That is going to go on our memorize or die. Okay, so how do we figure out what the form of that rate law is going to be? We need to determine the power to which each reactant concentration must be raised in the rate law, which means we got to come up with the order. And everybody's like, what is order? I don't understand it. It's very easy. We determine the order by looking at how does changing the concentration change the rate. If I double the concentration, does the rate of the reaction double? Does the rate of the reaction quadruple? What happens to it? If I double the concentration of the reactants and nothing happens to the rate, that tells me something else. So whenever you want to think about order, and what does order mean? It's how does changing the concentration change the rate? So how do you determine rate law? There are two ways to determine the rate law, and they're easy to figure out which method you have to use. You got to look at the data that they give you. The data can only be used in one way. And so we have one of the methods that's called the method of initial rates, and it's really easy to remember what you need for the method of initial rates. You have to have initial concentrations. You have to have initial rates to use the method of initial rates for this. As well, you're going to have a lot of different experimental data to look at, but notice everything in purple, initial, initial, initial. You have to have those initial rates and initial concentrations. A secondary method that we have to have is if you have concentration and time. Notice they both share concentration in common, but we switch out to looking at a time unit instead. And there's also one other key thing that's different here. There's only one reactant. So method of initial rates can be used for one reactant. That's entirely possible. But it's more commonly used when we have two or three reactants. The graphical method is for one reactant only. We won't be using it for multiple reactants. And the graphical method also, notice I put out here or chart. If you go online to the wiki page, you'll see Kinetics Made Easy chart. All of that stuff that's on that chart can be used with the graphical method once you figure out the order. So you get a lot of useful things to use. So once again, it's a way to experimentally determine the form of the rate law with the method of initial rates. The initial rate is that point where we have mixed our reactants together and they haven't changed very much and we don't get any product to worry about. So we're picking a very specific moment in time to look at. What you're getting here on purple, look for the data table to list initial concentrations. And you may see it, we saw this back before in equilibrium. You may see a sub-zero outside the brackets. That means initial conditions as well. And definitely see the initial rates there. You'll also see that there's a lot of data given to you. There'll be several different experiments or several different trials that they've done. You'll notice that there'll be some changing of the concentrations, and therefore you'll see some rates that might be different as well. Well, combining all of that information, we can come up with our rate law, come up with our orders. Here's just a real generic form, once again, of a rate law. Rate equals K. Every rate law starts like that. And if we had 3 different reactants, this is what this might look like. The star here means there's something else we can calculate. We can not only come up with the individual orders here, we can also come up with the overall order. And this is a real brain buster to calculate this. You take N plus M plus P. You just add up all your orders, and that gives you the overall order of the reaction. Okay, so if you have your textbook, you're going to want to go to page 562. Now, for those of you who don't have your textbook because you forgot and you left it here at school, over on the next slide, I've put a picture of the data that we're going to be looking at. The key to method of initial rates is you want to compare 2 experiments where the reactant you're studying is changing, but every other thing is constant, not the rate, but all the other reactants are constant. So you want, for the method of initial reactants, you want one reactant to change. Other reactants are constant. Now, this is your ideal situation. That's what you really want to have happen. It doesn't have to be that way. You can actually calculate rate laws with 2 reactants changing. That's something I'll show you in class. We're going to focus really on the real basic one so far, where we just have 1 changing. Oops. Okay, so this is from your textbook on that page 562. And one of the things I want you to notice first is initial, 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 initial. They are all, everything is initial. And so when you see that, that tells you that this has to be the method of initial rates. And you'll notice we have our bromate, our bromide, and our hydrogen are 3 reactants, and we don't even have any product data in this one. Be careful, sometimes they're tricky and they throw some product data in. And so what we want to do is, using this data that they've given us, we want to find the rate law. We want to calculate the overall order, and we want to come up with the value of K. So just exactly what I said, the first 3 things we're always going to do whenever we come up against a rate law problem: order, rate law, K. We always have to do all of those things every single time. So I'm going to go ahead and I'm going to kind of be going back and forth between the slides here for a bit, so hopefully this won't be too confusing. I'm going to write up here what our generic rate law is going to look like before we get our orders put in. So we have rate equals K, and we had bromate, and we need to find its order. Bromide, and we need to find its order. Now that looks like a 7. I tried to fix that, and that was a disaster. Bromide and its order, and hydrogen and its order. And whoops, there's the bell. See, I really am here at school. What we want to do is let's go ahead and start with our bromate first. Let's come up and figure out what bromate's order is going to be. Now, gonna go, hopefully, we're gonna do this pretty seamlessly. We're gonna go back to the last slide. And on bromate, what we want to use is we want to find 2 experiments where our bromate is changing and our bromide and our hydrogen are constant. So here with experiment 1 and experiment 2, our bromate is changing. And look here, our bromide and our hydrogen, they're constant. That's our goal. So method of initial rates, the best case scenario is the reactant you're studying is changing, and the 2 that you don't want to study, that you're not looking at, they're going to stay constant. And so that's what we've got in this particular case with experiment 1 and experiment 2. So let's go back to where I was. Oh, well, that's not fun. Let's go back. It took away my writing. I didn't think it would do that. Okay. We're having a small technical difficulty here. And you can all laugh at me while I'm trying to get this back. Let's go here to see. Okay. There we are. We got that one. That one's okay. Okay, now. Okay. I will rewrite what they took away. We had our bromate, our bromide, and our hydrogen, and I may have changed those orders up there, but it doesn't really matter. Okay, so on our bromate, we looked and we saw that experiment 1 and 2 had our bromate changing and our bromide and our hydrogen being held constant. And we want to compare these. Now, I like my math to be easy, so I'm going to compare, let me rewrite that. I'm going to compare experiment 2 to experiment 1. And what I'm going to do for that is I'm going to have the rate or the information for experiment 2 over experiment number 1. And I'm going to put in all of their concentrations. Have the bromate, the bromide, and the hydrogen. So, and notice I'm putting them one over top of each other. And M, N, P. M, N, P. Okay, so let's fill in. Rate 2 was 1.6 times 10 to the negative third. Rate 1 was 8.0 times 10 to the negative fourth. Now, our bromate, which was changing, in experiment number 2, it was 0.2. In experiment number 1, it was 0.1. And then for our bromide, both times it was 0.1. And same thing for our hydrogen. Both times it was 0.1 as well. Well, what happens is the ones that aren't changing, we can go ahead and just cross those out. They divide themselves out. What we need to do here is just deal with the math that's going on. 1.6 times 10 to the negative third divided by 8 times 10 to the negative fourth. Or when I look at this problem, I see 16 divided by 8, and 16 divided by 8 is 2. And then we have 0.2 divided by 0.1. Well, when I look at this problem, I go 20 divided by 10 is 2 raised to the m. And now we got to figure out what m is. Well, 2 raised to what power will give you 2? And 2 raised to a 1 will give us 2. So 2 to the first is 2. And so now we know our order of our reaction. Our order for our bromate is no longer unknown. Our bromate is now first order. We have figured out one of them. For our bromide, we're going to go ahead and we're going to do the exact same thing. We are going to look for 2 reactions that we can have the bromate this time and the hydrogen being constant while our bromide changes. And I am not going to go back for fear that I might actually lose what I have written here. So let's go look at your textbook. So we're looking for 2 experiments where our bromate and our hydrogen are constant and our bromide is changing. And if you go and look at experiment 2 and experiment 3, that matches our criteria. From experiment 2 to experiment 3, our bromate and our hydrogen are constant, while our bromide has changed. So we're going to go through the same process that we did here, except now we're going to use our, we're going to go to our next part. We're going to look at our bromide now. So same thing. I'm going to do rate 3 over rate 2. You don't have to. You can do rate 2 over rate 3. Rate 3 over rate 2. The rate for our reaction on rate 3 was 3.2 times 10 to the negative third. And for rate 2, it was 1.6 times 10 to the negative third. Get ready to fill in all of our information. For bromate, it was 0.2 on both experiments. If you wanted to, we already know its order, so we could plug it in up there. Bromide was 0.2 in experiment 3 and 0.1 in experiment 2. And our hydrogen was 0.1 in both cases. So just like before, we're going to cross out those things that are constant. Get rid of those. And do our division. Now, when I look at this one, I go, oh, 32 divided by 16. That's a 2. 20 divided by 10, that's a 2. Raised to the n, well, this is the exact same order as our last problem. 2 raised to what power gives us 2? Well, 1 is our power. So our bromide is first order. So far we have our bromate, which is first order, our bromide, which is first order, and now we're going to finish up with our hydrogen and figure out its order. And so we go back to looking at our experiments and we do the exact same thing again. This time we want hydrogen to change, and if possible, we want our bromate and our bromide to be constant. So pretty much we have to use experiment number 4 because that's the only one that has a different concentration for our hydrogen. So now we got to look at other ones to see what would be good to use. And if we use experiment 1, then our bromate and our bromide will be constant and our hydrogen will change this time. So we're going to do rate 4 over rate 1. Rate 4 is 3.2 times 10 to the negative third. Rate 1 is 8.0 times 10 to the negative fourth. And now let's go ahead and plug in our concentrations. We wanted bromate and bromide to be constant this time, and they were. They were all 0.1. And we could go ahead, we know their orders even, we could plug those in. And we wanted our hydrogen to change this time, which it did. It was 0.2 over 0.1. Cross out the constants. And some of you are saying, well, if they're constant, do I even have to write them? If you want to take the shortcut and not even write the things that are constant, you can, because you end up crossing them out anyway. So when I look at the rates, I look at that and go, oh, that's 32 divided by 8, and that gives me 4. And I got 20 divided by 10 again, that's 2. And 2 raised to what power gives me 4? Well, if I square 2, I get 4. So the order on this one this time is second order. So my hydrogen, this was my hydrogen here. It is second order. So now that I have all my orders, remember our first step was I got to get my orders. Now I can write my rate law. Rate equals K times our bromate, which is first order, our bromide, which is first order, and our hydrogen, which is second order. And so here we have the second thing we need to do is have a rate law, and that's what it looks like. Now, at the same time, if you wanted to go ahead and calculate your overall order, that's not difficult. All you got to do to calculate overall order is add up your orders. So our overall order equals 4. Now, the last thing we need to do is come up with our value of K, come up with our rate constant. And I need to see if I can add, whoops, that's not what I wanted to do. Add another slide in. Let's go down here. There we go. Okay, so we're going to need a little bit more space here. So let's go here. And we are going to temporarily end the show so that I can add in the easiest way to know add in a new slide. There we go. Now we are going to go from here. Okay. A little technical. Little tech. Of course, it went on to the next slide. That's my luck. Okay, there we go. Sorry about that little spring break. I got spring break brain. Okay, let's calculate our K. So let me write that rate law up for us again, because you have to have the orders, and then you have to have the rate law in order to be able to calculate, calculate your K. Because there is a method that you have to follow. Order, rate law, K. And K is basically filling in values into this equation that we have up here, this rate law, picking any experiment you want to, plugging in all the values that you can. The only thing you can't plug in is your K, and then you solve. I typically always just choose the first experiment, but you can choose any experiment that you want to, because just like at equilibrium, the only thing that ever changed K was temperature. That same thing is true here in kinetics. Your K value will always be the same until you change the temperature. So you can choose any of them that you want. I'm going to use experiment number 1. And first, I'm actually going to rearrange my equation a little bit to get K by itself, just for ease. This helps with the unit analysis as well, because the units are just yucky on these. Okay, so using experiment number 1, I have 8.0 times 10 to negative 4th moles per liter second over 0.1, and I'm going to put my units in here because I've got to do a unit analysis. Moles over liters, 0.1 moles over liters, and 0.1 moles over liters, but be careful, this one is squared. Now, you probably won't have any trouble coming up with the value for K, because it's just a division step, and so you'll get the 8.0 pretty easy. The units are kind of a mess, and so we'll do a little bit of a unit analysis on this problem. And then when we're back in class, I'll actually teach you some cheating methods to come up with it as well. So for our unit analysis, we have moles over liter second divided by, now we got a mole times mole per liter times a mole per liter times a mole per liter squared. That is actually moles to the 4th over liters to the 4th. Well, now what do? We flip what we have on the bottom, liters to the 4th over moles to the 4th. So we flipped that. And now cancel out whatever you can cancel out. This liter cancels out the 4th and leaves it a cubed. This mole cancels out the 4th and leaves it a cubed. So we end up with liters cubed per mole cubed second. That's a horrible unit. Liters cubed per moles cubed second. So see, that's the worst part about rate laws, is coming up with what that K is. And when we get back into class and we've worked through more problems, I can give you a little cheater method for getting through that. It does get easier on those units. Okay, so that's the method of initial rates, and we'll work a bunch of those problems in class, and they definitely will get easier and easier for you. The second method that we have is the graphical method. Couple things to remember. The data will only be time and concentration, and there'll also only be one reactant. One of the things you'll find though with the graphical method is sometimes they will say in the actual question, by graphing this data, it was found this reaction was first order. So you don't have to graph it. They just told you it was first order. So it's really important that you read carefully because a lot of times they give away a lot of stuff. So that's where the Kinetics Made Easy chart will come in really handy for you. We're also going to be introduced to a couple different rate laws here. The other rate law that we looked at, where we just wrote rate equals K and then the concentrations, that's also known as the differential rate law. The integrated rate law is one that we specifically use when we have found through the graphing method, we have come up with the regular rate law. Well, you can also come up with an integrated rate law. And this is always reactions involving a single reactant that have the same rate law, rate equals K times the concentration to whatever order. So every graphical method problem you work is going to look like this. You're just going to have a different order. It's going to either be 0, 1, or 2. But once you get that rate law, the differential rate law, this one is the differential, or AKA we just call it rate law. Once you have that one, then it kind of opens up a world of other things you can do. And the next one is the integrated rate law. And the integrated rate law integrates time into the rate law. We're going to put time into it. Okay, so most of this stuff over these next few slides is also on your reactions made easy. So I'm going to go through this pretty quickly. Let me let's go ahead and put some things up here. Okay, first order rate laws. In a first order rate law, doubling the reactant doubles the product. And so if we were going to write this rate law for this first order rate law, rate equals K times concentration in 205, and notice there's no order there, it's an understood one. You can write the one in if you want. Now, when we integrate that with time, it takes on a different look to it. But the first order integrated rate law has all the same components. It always starts the natural log of your reactant at the time that you're concerned with equals negative KT, that K is the rate constant that we would have previously determined at the time we're concerned with, plus the natural log of the concentration of a reaction at time 0. That initial time is going to be important to us as well. And if you go to your chart, Kinetics Made Easy, you'll see, I think I have on there, natural log of A equals negative KT plus the natural log of A0. We just plug an A in there. Every first order integrated rate law looks exactly the same. Okay, so let's get this. Let me get a few more things up here. Okay, I think that's everything we need. Okay, so there's your first order rate law. They all look the same from the graphical method. There is the integrated first order rate law that I was talking about. We integrated time into it. And what's great about the integrated rate law, it pretty much lets you do whatever you want to. You can solve for all kinds of different things for it. You could actually use it to solve for K if you wanted to. If A is the initial concentration is known and K are known, the concentration of A at any time can be calculated. Now, what is like so totally cool about this equation is it is in the form you are finally, here it goes, you are going to use algebra. Mark this day on your calendar. We are actually using algebra. This equation is in the form of a line. Y equals mx plus b forms a straight line graph. Our y-intercept is the natural log of concentration of A. Our x-intercept is our time. Sorry. I did that wrong. I'm having spring break brain. What we're going to graph along the y, is our natural log of concentration of A. Along our x, we're going to graph our time. Our slope is going to be equal to the negative rate constant. And there, b, our y-intercept, is going to be the natural log of A at time 0. First order always gives a straight line graph by plotting this. So when we're doing the graphical method and you want to know if it's first order or not, that's what you have to graph, the natural log of A versus time. There's another way to express this. I don't think you're ever going to use this, so you could probably just mark that off of your memory list. Here is just a sample of what the data would look like. For this, notice the difference here. We just have concentration and time. The word initial appears absolutely nowhere on this. Now, I'm not going to attempt to have us try and give you an online lecture on how to graph this. Bring your graphing calculators to class on Tuesday, and we'll do this one in class. I don't think it's going to translate well via online lecture. Oh, apparently I put some sound in on this one. Half-life of a reactant. So there are really kind of 3 rate laws that you can get and use. The differential rate law, which is AKA just rate law, that first one we come up with. Once you know it's what form of the rate law you have, whether it's first order, second order, or 0 order, then you get the integrated rate law, and that's you put time into it. But you can also get the half-life equation as well, the first order reaction, half-life law, rate law. T1 half equals 0.693 divided by K, that rate constant. So remember when I said you get your order, you get your rate law, and then you get your K. You have to have K. Everything else revolves around using that K in some way or another. So there is that one. So I wanted to show you something because you can graph to find out the order, but sometimes they just tell you what the order is going to be. And so here we have a certain first order reaction. Do not ignore this. This now tells me what things I'm allowed to use from my Kinetics Made Easy chart. I can use anything under first order. I now know the rate law is going to be rate equals K times concentration of A. I know it's going to be the natural log of A equals negative K T plus the natural log of A at time 0 for my integrated rate law, and I now know what half-life equation I can use. Just reading those 3 words, first order reaction, gives me all of that information. I have those 3 rate laws. Okay, it has a half-life of 20 minutes. Calculate the rate constant for this reaction and how much time is required for this reaction to be 75% complete. Okay, so I need the rate constant first, and they've given me the half-life, so that's my go-to equation to use there. I'm going to erase to make a little bit more space. T1/2 is 0.693 divided by K. I need to figure out what K is. I'm going to flip-flop. K is 0.693 divided by T1/2. 0.693 divided by 20 minutes. And that gives me a value of K, which equals 0.0347 inverse minutes, because minutes is on the bottom. So now I have my K value. So I know my laws. I know my order first. They gave that to me. Know my laws. I can use any first order law to solve for whatever I need. And I've got my K now. So now I can do that fourth part, whatever I want to with it. So the second thing they ask us here is how much time is required for this reaction to be 75% complete. Okay, there's a really important word in this sentence. Time. I'm looking for time. Well, time means integrated rate law, because that's the only one that's got time put into it. So I want to use my first order integrated rate law. It is 75% complete. Now this is where sometimes we have a little bit of trouble kind of figuring out, we don't have any concentrations to plug in. Well, you can actually use your concentration, your percentages as your concentration. So look at this very carefully. We have reactant A, and we are going to turn it into product B. Now, at time 0, what percentage of A do we have? Well, it's time 0. Nothing's happened, so we have to have 100% of it. Now, when this is 75% complete, how much of A do we have left? Because remember, it's all about the reactant. So our A is going to go from having 100%, it's 75%, it's going to go down to 25%. That means we've taken 75% complete, means we've turned 75% of it in from A into B, so we only have 25% left. Now, using our integrated rate law, we're going to take the natural log of A at our time that we're concerned with when we're 75% complete. So we only have 25% left. We have our K from over on our previous problem. I'm going to leave out the unit for now because it's going to get a little messy. And we initially had 100%. Now, do not try and do this all in one step. Break it down. Take the natural log of 29, negative 0.0347 t. Take the natural log of 100. Okay. Put your like terms together. So I'm going to subtract my 0.4605 from both sides. Negative 1.386 equals negative 0.0347 t. It's good they're both negative, because if one was positive and one was negative, we can't have negative time. That would be a disaster. And then solve for our time, and we end up with 40. And if you go back and you look at your K, it'll tell you what time unit to use, and it takes 40 minutes to reduce this by 75%. Now, some of you may have seen another little trick to answering this one. If you did, that's okay. You can use that little trick as well, but I'm not going to announce that one to the world, how that one worked. Okay, I'm pretty much thinking the rest of this PowerPoint is on your charts made, your Kinetics Made Easy one. So I don't think I'm going to talk too much about this because once you know how to use that chart, you can pretty much do anything. So we'll talk more about these in class. So check that chart out. That chart gives you everything you need to know. And I think the last little bit, yeah, I'm just going to talk about this last little bit here. Chemical reactions speed up when temperatures increased. All rate constants show an exponential increase with absolute temperature. Remember, any K we ever talk about, whether it's equilibrium K or rate K, the only thing that ever changes K is temperature. And in rate laws, it changes it exponentially when we change the temperature. Um, you've probably learned about the collision model last year. And in the collision model last year, we would have talked about these two components. First one kind of makes sense when it's called the collision model. Molecules must collide in order to react. Duh. Molecules must possess a minimum amount of energy for collisions to be successful, and that's known as our activation energy. And we've actually kind of talked about that a little bit because we've mentioned a catalyst here and there when we're talking about equilibrium. But then there's this other part that we haven't really talked about yet that's necessary for the collision model, and this is the molecular orientation. The reactants must be properly oriented to allow formation of new bonds of the product. So not only do they have to be collide and have the activation energy, you have to have the right parts of the molecules to actually interact with one another in order. So it's kind of amazing that a chemical reaction ever takes place when all of these things have to happen. That we will talk about more in class on Tuesday. And that's it. I think this one was a little long. I'm so sorry, but 9 snow days killed us, so you're going to have to do a little extra work at home. I'll see you when you get back. I hope you had a nice spring break.